Let's jump into our next section to understand what's the model architecture for this word-to-vec word embedding. Alright, so what I have tried to draw one neural network. It's a very rough version of it. Okay, so before I start explaining how this model looks like, so we need to understand three very important terms. One is vocabulary size. Okay, vocabulary size is the size of the unique words we are going to consider in our training process. Okay, in our one corpus or one document may contain 20,000 unique words, but we may not consider all of them. We will set some parameters, like if the word frequency is less than 5, then we can ignore those words, and similar sort of things, filter we are going to apply. So finally we need to consider a size of our vocabulary. Okay, so that means the number of unique words we are going to consider. Normally those vocabulary words are indexed in such a way so that the most frequent word will come first, and then second most frequent word, and so on it will go. Okay, so we will have 2 or 3 additional field or positions where we are going to consider the unknown words and start of the sentence, similar sort of things, and I forgot the other one. So the takeaway is that vocabulary words are the list of unique words which we are going to consider for our model. Okay, in this particular example we have considered a vocabulary size of 10,000. Alright, so next point is that dimensions. Okay, they call it in different name in different books or different presentation. So for your understanding, is the dimension is that higher dimensional space where you are going to represent each of your ports. Okay, earlier in the 3-dimension diagram we have pointed our January, February, different months, and name of the cities and name of the countries. In that particular case we had dimension of 3. 3 is very low in this particular case, and in this word-to-vec model normally they consider minimum 25 till 300 or maybe higher than that. Okay, so in that higher dimension space each of those words are represented. So that is another term which I have used as the dimension. So another term is that softmax. Softmax is taking a number and distributing those numbers in a probability distribution manner. Okay, so highest number will have the highest probability and the lowest number will have the lowest probability. If you another presentations which I did a few days back, you can go to that deep learning sections and you can watch that softmax and other kind of neural network layer presentations where you will understand what is the deep inside of the softmax concept. Okay, so for now you can take it as that this is the way to transform a list of number to a probability distributions. Okay, so let's come back here. So this word-to-vec is a neural network model. This cannot be a deep neural network model because it contains only one hidden layer. Okay, in neural network we have the input layer, then the hidden layers, a list of hidden layers, then the output layer. In this particular case we have total 3 layers. One is input layer, one is hidden layer, and there is output layer. Okay, so as we have one hidden layer, so it is a very shallow neural network, but it may have multiple or very big number of neurons depending on the dimensions we are using. Alright, so in this particular case we have, this is the input layer, this is the output layer, these are the individual neurons, these are individual neurons, these are also individual neurons, this is hidden layer. The size of the hidden layer is the dimensions where we are going to represent our each words. It's the dimension of the vector space where we are going to represent each of these individual words. So that is the exact size of our hidden layer. The size of the output layer, this is output layer, is the size of our vocabulary. Okay, in this particular case we have taken 10,000 vocabulary. So the size of the output word is the size of our vocabulary, and that is true for our input layer also. Okay, input layer and output layer will have the size of our vocabulary, that many number of neurons. Okay. Another point is that we don't have any activations in our hidden layer. We don't have any activations. Okay. So basically the net input in other term we are going to consider from our hidden layer, and we are going to send those content to our output layer. In output layer we have softmax activations. Let me write it down. I have written it here. Okay. In output layer we have our softmax activation. Okay. So the final content which we are going to get from all this model, all these calculations, is a list of 10,000 values, which is basically the probability distributions for all those unique words. Okay. In skip-gram model we are going to pass the target word as input. How? That is what I am going to explain a little later. We are going to pass the target word as input, and it will do all the calculations, and it is going to give you the list of context words in the form of higher probabilities. You can sort all these words depending on their probability values, and you can pick top 5, top 10 and top 100, whatever you need. Okay, but this is where you will have the probabilities for each of the words in the vocabulary to belong as the context word of the target word. Okay. Now, input. How this input will look like? Input will have total 10,000 values. Only the target word will have 1, and rest of the field will have zeros. Okay. For example, Soviet. This index is 3, for example, 2 in Python term will have a Soviet. It is representing Soviet. So it will have 1 and rest will have 0. Okay. This is how this is in other term it is called as one-hot vector encoding. One-hot encoding. Okay. These input will have only 1 for the target word, and the rest of the words should be 0. It will be passed to the hidden layer. Hidden layer will do all these calculations. We'll try to understand something. It will send those contents to the output layer. Output layer will also produce the probabilities of the list of words, probabilities for each of the words in the vocabularies to be the context word for this target word Soviet. Okay. For example, suppose this is the word which is maybe Russia. Okay. So from general understanding point of view, if we are talking about one of the word is Soviet, so the probability of the other word Russia should have the highest probability than anything else. Okay. So you will see normally that this particular field will have highest values than anything else we have in this probability distribution. Maybe other word is mango. Okay. Maybe watermelon. Okay. But compared to those, Russia will have the highest values as a probability to belong as the context word of the word Soviet. Alright, so this is what we have. And during our training process, we just go through each sentence in the corpus. We create a list of target word and the corresponding context word, and we pass all those indexes to this model, and the model will try to produce and will have the backward propagations. We'll adjust all these values inside, and we'll finalize the context of the weights for each of these neurons. Okay. Now, interestingly, in this particular word to weight model, the way we are training our model, we are not going to use it in the similar way. Our target is to make this model to understand the weights for each and every neurons, and then forget about why we created it. As far as we have got the weights for each of these neurons. Okay. Interestingly, the weights for the hidden layers is basically the higher dimensional representations of those words in those 300 dimensional space. Okay, that is something like word embedding in other term they call it. Okay, so the key takeaway is that once the training is done, we are not going to use this model for the prediction point of view. We are going to understand the content of those weights, and we are going to use it as a higher dimensional vector representation for those each individual words. Okay, so next sections I'm going to show you like how it is going to use those weights and how it is going to produce the output. Okay, so that you will have clear understanding about this whole end-to-end modeling. Okay, let me draw something.